a total amount of positive charge, Q, big Q, spread out onto a non-conducting flat circular annulus of inner radius A and outer radius B, so basically like a washer shape. Charge distributed so that the charge density is given by sigma equals K over R cubed, where R is the distance from the center of the disk to any point on said disk. Show that with voltage equals 0 and infinity, the potential at the center of the annulus is given by this equation. Okay, so first start by drawing a picture. We got a picture kind of like so. A washer, a disc if you will, a disc with a hole in it, a disc minus the interior disc. So we have A, B. I know, kind of small. You get the idea though. Yeah, and it looks like we're just going to start from the middle and integrate outwards. So we want to find the potential, i.e. voltage. And to do that, we're going to look at everything as point charges, because if you look hard enough, everything in life is a point charge. So I'm going to say V equals KQ over R. This is just the potential for 2 point charges and over a point charge. And so we can say that if we have for a small bit of voltage, we get K, Coulomb's constant, which is different than this K. We're going to have to keep that in mind. Small bit of charge Q over R. All right? And for our small bit of Q, we're going to say that that is related to sigma, the surface charge density of our washer. And sigma, surface charge density, is defined as a small bit of charge for a small bit of area. And the area we're going to look at is small little circles going on the way out. So the area, basically starting in the middle, working our way out from A to B. And the thickness right here, that's going to be delta R. And around it is going to be 2 pi R. So the area is going to be 2 pi R times delta R. So another way of thinking this is we cut right there, we stretch it out or lay it out. This length, which is going to be the circumference, is 2 pi R, and this is going to be delta R. And your thought process is, well, really, the inside is going to be a little bit smaller. It'll be 2 pi R, maybe minus delta R or something. R minus delta R is basically the same as R. So I know there's some nuance there. We're not going to think too deeply on that. All right, so we get delta Q here all over 2 pi R times delta R. We need to have 2 R's because this is an area. So from dimensional analysis, area is measured in meters squared. So we got R, delta R, good. But we're not really all that concerned with sigma. We're concerned with delta Q. That's what we want here. That's our goal in life because we want this delta Q up here. And so what we're going to say is delta Q, a small bit of Q, is sigma surface charge density, 2 pi R times delta R. We're now going to put this into our... Actually, I'm going to do this a little bit differently. Hup. Everything I said, totally true, 100%. But we can make this a little bit easier. We know that sigma equals K over R cubed. There we go. And so we're just going to ignore sigma at this point, and we're just going to use this portion. So now, get a color with better contrast. Ooh, I like yellow. It's so bright, though. We're going to say that, ooh, that is bright. Delta Q equals K 2 pi R delta R all over R cubed. And I'll do some canceling. That becomes R squared, gets rid of that R up top. And then I'm going to rewrite this K. No, we're going to leave that K the way it is. I'm going to rewrite this K up here, because this is Coulomb's constant K, different than that K. This is going to be 1 over 4 pi epsilon naught. And I'm just going to rewrite it to minimize confusion with the K they gave us. All right. So now we're going to put everything together. Well, most things together. So we're going to have delta V, which is a small bit of voltage. We know that's going to be 1 over 4 pi epsilon naught, what I formerly referred to as Coulomb's constant, or K, but which was discarded due to convenience. I know, it makes it sound harsh when I say that. And we're going to put in delta Q, which is K, different K, 2 pi delta R over R squared. And then we need to make sure we remember that R right there. So we're going to multiply this by another R. We're going to rearrange this to make life more convenient. Start by canceling 2 pi and 4 pi gives us 2. So we're going to have K over 2 epsilon naught divided by R cubed, which I'm going to say is the same as multiplied by R to the negative 3. That way it's just more obviously going to be the power rule for when we integrate this. All right, so I think that's good. I think we're good. So now, integrate both sides. Integrate, integrate. And so V, we're going to integrate from A to B. So we're going to do it from the inner part to the outer part. Because it's between A and B is where the surface charge density, sigma, is defined as K over R cubed. That's where our assumptions hold. So now, let's see here. We'll do K over 2 epsilon naught. Integral of R to the negative third is R to the negative second divided by negative 2. And it's going to be evaluated from A to B. So A to B. And then we plug in B there. I'm going to do some magic here. K over 2, I'm going to say 4 epsilon naught, because 2 times 2. And then normally this would be 1 over B squared minus 1 over A squared. But I'm going to do 1 over A squared minus 1 over B squared. And what I did there was I took this negative and flipped the limits of integration. So we got that part. So the issue then, so this is our answer, but they want us to show it in terms of Q without the constant K, which we can totally do, I think. We're going to go for that. So I'm going to take this part right here, which we talked about earlier, move this down here, and I'm going to rewrite this just one more time, just to get rid of the, so this will be 2 pi K, not Coulomb's constant, R to the negative second, delta R. So delta Q equals that. So if we integrate both sides, we get the integral of delta Q is going to give us total Q, big Q. Black wouldn't work very well. We're going to do orange. Big Q equals 2 pi K integral A to B of R to the negative second dr. And I just converted the delta R to dr, going from very small difference in radius to an infinitesimally small radius. And so then this becomes 2 pi K R to the negative 1 over negative 1, evaluated from A to B. What I'm going to do then is I'm going to get rid of the negative to flip the limits of integration. So now we're going to go from B to A. And this gives us, actually I'll do it down here. Q equals 2 pi K 1 over A minus 1 over B. And we'll do little parentheses there, well, brackets. But we don't care what Q equals, we want to convert K to Q. So we're going to, does this color work? Ooh, that's kind of bright. Yeah, I like that. We're going to go with that. Kind of an eggshell white. Actually, I'm going to do this one more time. I'm going to combine these through a common denominator, 2 pi K. We're going to multiply both sides. We're going to multiply the left part by B over B. So this would be times B over B. This is probably multiplied by A over A. So that's going to give us B minus A all over AB, which is the same as BA. That makes it easier to solve for K. So K is going to be Q over 2 pi times AB all over B minus A. And I'll put the brackets there, though not entirely necessary. Seems reasonable. Okay, so now we know what K equals, and we know what V equals, so we can combine these together. And so combine this, combine that, and for that I'm going to use a new color. Use a lot of light blue. Yes, kind of the orange is yellow. So voltage equals K, which we now know is Q over 2 pi AB all over B minus A. That's K, but we're just going to have the 1 over 4 epsilon naught still. And we're going to have, I'm going to do the same thing with this. This is going to be K. I'm going to do the same thing of combining the two fractions with a common denominator. So this becomes B squared minus A squared all over AB, A squared B squared, which is the same as AB squared. And then I'm going to rewrite this one more time, since on the top we have a difference of squares. K over 4 epsilon naught, B plus A, and we'll do a B minus A. There we go. All over AB squared. There we go. So we have our 1 over 4 epsilon naught. That's K. We'll do B plus A. B, that's terrible. B minus A all over AB quantity squared. Okay, so this is going to be our final voltage answer here. We can just simplify things a little bit, I believe. So we have an AB, everything's multiplied together, so we can get rid of the AB. We have a B minus A, we have a B minus A, and the 2 and the 4 can combine together. So we're going to have Q over 8 pi. Is there supposed to be a pi there? Maybe. I don't know. We'll see what happens. Times B plus A all over AB. And we'll see how close that is to the answer that we actually want. Come back up here. Yep, there's it. Yes. Q 8 pi epsilon naught B plus A. Yeah, it's the I don't even know what that property is called, but A plus B, B plus A are the same thing. A times B. Okay. So we did get the correct answer, which means we probably did it correctly. And that's kind of the nice thing about these proof questions is it's sometimes you're obviously wrong, which is convenient. All right, to recap what we did here, we wanted to find the voltage of this shape of a washer, of a disk minus disk. And to do that, we started with the idea of the voltage for a point charge. Voltage equals KQ over R. And when we have a circle like this, it's also going to be the voltage for a circle or a sphere. And so what we did then is we could say that, all right, we're going to have a small bit of voltage for a small bit of charge, that delta Q. And we took that delta Q and we were able to, let's see here. We were able to use sigma, the surface charge density, which was delta Q over delta area. We then mathed that out. We found what delta Q would be, and we found the voltage in terms of the constant K they gave us. Now the only catch there was they didn't want to do it in terms of K. They wanted the answer in terms of total charge Q. So like, all right, go back to the delta Q that we found, integrate over all that, and we know that we find the total amount of delta Q's that we have, add them all up, we get the total Q. And that we're going to use that as a constant, as a constant, yep, total charge Q. We found that in terms of K. Plug that value back in for the K we have, did some more math, did difference of squares, never thought that'd come in handy, guess it did. Did some more math, and we got the final answer. So that's how I'd approach this problem. Hope it helped. See you next time.